All right, here's the recording in progress. All right, so we're here. We're done with the first exam. You should have gotten an email back from me about the exam, and hopefully you got the thing that I sent. I ended up curving the exam. There were many students who were not able to finish the exam, although many of you did. And there were several of you who got to say 6 or 7 questions, and you did them well, but then there was nothing after that. So I knew, for the most part, you knew what happened, but you ran out of time. So as a result, I ended up curving the exam. So the explanation again, you got a raw score, the score that I went through the first pass, and then I ended up curving it. So then your score was higher. If you already were getting an A anyway, it was only a little bit higher. But for some of you who were in the possibly B or C range, the curving made it much higher in general. And so I have my own curving formula based on how I thought you knew the material. I guess maybe I should have made the exam an hour and a half or 2 hours, but be that as it may, what happened was what happened, and there we go. Okay, other things about the exam, I have to emphasize, you have to do the problems the way we did it in class. So question 2, the area of the triangle, some of you did it completely in a non-calculus format. The question said specifically use calculus, and this is a calculus class, not a geometry class. And I could have very easily given you some functions where you couldn't have just done algebra or geometry. The basic idea was to show it by means of calculus, and that was much more work involved. Okay, so that's what I could say about that and about the test overall. Okay, my grading scale is 90, 80, 70, 60. 90 is an A, 80 is a B, 70 is a C, 60 is a D. And if you're off by 1 point, that's a minus. So 89 would be A minus, 79 would be B minus. We're not actually allowed to give C minuses. And then another point down would be the plus grade. So 88% would be B plus, 78% would be C plus, and so forth. Okay, so that's the way you should think of it. All right, so schedule-wise, so we're already into 3 weeks. So quiz, test for the second exam. Okay, and again, it looks like we're doing about 2 days per section. So 2 days for 7-1, 2 days for 7-2. Next quiz will be 7-1, 7-2. Keep in mind, it's already Tuesday. So quiz. So it looks like our second exam is on Friday the 24th, 7.1, 2, 3, 4, 7, and 8. Okay, so I think we can keep up the schedule from here. So we have 7-1 and 7-2 for this week. Again, it's already Tuesday. This is a complete side note. I always felt this way. Whenever you had a 3-day weekend like Labor Day, and then you have to go back to school or work, so, oh man, the weekend's over, I got to go back on Tuesday. Yeah, but to me, it was better because when you go back, you only have to go back for 4 days, right? Not 5 days. It isn't a 3-day weekend, and then you have 5 working days. You have a 3-day weekend, and even when you have to go back, you only have 4 days, right? So it's like, well, the benefits still continue because my mind thinks like, oh, this is Monday. It's the first day of the week, but it actually isn't. It's already Tuesday. So we're still fairly close to the next weekend. I don't know, that's the way I look at it. You don't have to agree with me, obviously, but when you have a 3-day weekend, you go back, it isn't Monday. You don't have to go back 5 days, you go back only 4 days. So anyway, that's my little spiel on that, but which has absolutely nothing to do with math, but it's a way to think of the 3-day weekend. So the next time you have a 3-day weekend and you feel disappointed, oh, I got to go back. Well, remember, it's only 4 days until the next weekend, not 5 days. But anyway, okay, so that's where we are now. So we were doing integration by parts. I already did some of the problems, and I'll go back and do more problems with integration by parts. And when I introduced the topic at the time, I said, well, just take it kind of half-heartedly because we're still worrying about this test. But now you can get into it fully, hopefully. Okay. Quick notice for 7.7, the homework is down here. I didn't like any of the problems that were in the text, so I made it my own. You might say, I don't know what you're talking about here. That's okay. You're not supposed to know what it all means now, but you'll know hopefully later. And of course, therefore, don't look in the back of the book for any of these answers. There aren't any answers anywhere, but I'll end up doing 3 of these, maybe even 4, as we'll see. Okay. And now that you've had one exam, you know the format of the exams and turning in the homework. And a reminder, some of you didn't get your exam graded because you didn't turn in any homework, or I didn't get your ID. I need your ID. I need to know what you look like. I got it stored. So say, hey, here's your ID. And the person who's taking the test isn't the same person, right? What's going on here? So, yeah. All right. And then, of course, again, the rest of the time, I know there's few of you that are here synchronously right now, but many of you are not here. That's okay. Just watch the video later. The next time you actually have to show up for class is the next test. Okay. And then, you know, all this optional. You don't have to show up if you don't want to. I don't take row. And then you have to show up for the test. And same thing all the way through. Okay. So now let's finally get going with integration by parts. Some review and some new stuff. So integration by parts. This was derivation. You're not responsible for that. This is what you want to put on your next cheat sheet. Okay. And speaking of cheat sheets, don't throw away the cheat sheet from the first test. Right? Say, oh, I'm finished with it. You know, you throw it away. Keep it for the final exam. Okay. So that way you don't have to make a brand new one for chapter 6 for the final exam. You've already got it. Just, you know, keep it. All right. Integration by parts formula. Integral of u dv equals uv minus the integral of v du. This is the same thing as in the text, in case you want to see it. Page 472. Same thing. I would say don't even look at this one. It's the same thing. It's correct, but I think this is a lot shorter. Forget to memorize. So in one sense, you should be happy that we're under COVID, that you don't have to memorize this. Last time I taught this face-to-face, there was no such thing as COVID, and then I made everybody memorize this, but you don't have to memorize it now. Okay, and some rules to remember about picking a u and a dv. We would normally choose to differentiate ln x rather than integrate ln x. So if you see an ln x, you definitely want to differentiate, not integrate. And then we also said if you have to integrate a polynomial times either an exponential or a trig function, let u be the polynomial part and dv the rest. Okay, so I'll show you a lot more examples. Okay, problem 7. Integral of x squared plus 2x cosine x dx. I believe I already showed you the homework there, but if anybody still needs it, let me know. Okay, so again, I'm trying to make it where you can sort of survive without text, where I show you all the key pages and show you the homework pages and just go off of there. All right, so this looks like, let me check if this was actually the problem. Yeah. This looks like a polynomial with a trig function, polynomial trig. So we said under that circumstance, let u be the polynomial and dv the rest. So you might recall before the test, I did problem 3. And what happened was, let's see, yeah. I let u be the polynomial x, and then we had the trig function. And what happened was we started off with x times a trig function, and then we ended up with just a trig function. Okay, the whole idea behind integration by parts is to transform the integral into something minus another integral, and we hope this second integral got better. Okay, and it did. So x times a trig function. If I do it this way, I ended up with a trig function. Okay, if we tried the other way around, if I let u be the trig function and dv include the x dx, I started with x trig function. I ended up with x squared trig function. So it got worse. Didn't get any better. So that's the reason why we want to say, if you have a polynomial times either an exponential or a trig, let u be the polynomial part and dv the rest. Okay. And you can put that on your next cheat sheet also. So based off of that, here's a polynomial, let u be x squared plus 2x, dv is the rest, cosine x dx. So we're forcing this integral to look like the left-hand side, u dv. Then I get all these parts, u, v, du, dv, 4 parts. That's why it's integration by parts. And then I throw it into this. So u is x squared plus 2x, dv is cosine x dx. Integrate this, differentiate this side, integrate this side. Okay, so du is the derivative of this is 2x plus 2 dx. Integrate this side. It's almost like you sneak in a little funny s there to integrate. Integral of cosine is sine. V equals sine x. Okay, so I have u, v, du, and dv all here. Throw it into the formula. So u times v, x squared plus 2x sine x. That's u, v, minus the integral of v du. V du is that times that. So I have 2x plus 2 sine x dx. Okay. I'm going to call this I1. Okay, so my abbreviations, and this is just my own thing. Not every instructor does this. So if you have another instructor for your next calc class, they may not do this convention, but this is just my own thing. So in other words, I want you to do my thing, of course, but I think there's reasons for it. Let's see, did it get better? I started off with x squared plus 2x trig function. I now have 2x plus 2 trig function. Okay, it did get better. It went from being second degree to first degree. Okay. So now I have to integrate 2x plus 2 sine x dx. So I'm taking a little time out. I have to figure out I1. Okay. So the original integral, which I'm calling I, is x squared plus 2x sine x minus, there's a minus sign here, I1. So I can take a time out, figure out I1, and once I get I1, I plug it back into here. Okay. You computer science people may know this is, a little bit of recursion, where it's like you have to take a certain part of this and take a little time out to figure this out, and then once you figure that out, call this part of the program to bring it back over here and get back into the original. Okay. So it's almost like a brand new problem. I have to figure out I1. Once I figure out I1, I stick it in here and I get the final I, the original integral, I will label as I. So I, for me, is always the original integral. And then within the same problem, if I need to refer to another integral, I1, I2, I3, I4, and so on. Okay. So I now have to figure out I1. 2x plus 2 sine x dx. So integrate by parts again. U equals that. dv equals sine x dx. du equals 2 dx. V equals integral of the sine is negative cosine. Again, you have to be careful whether you're going the derivative route or anti-derivative route. So I1 is uv, same formula. U times v. So there's a negative 2x plus 2 cosine x minus the integral of v du. This times this is a negative 2 cosine x dx. And of course, that looks like a double negative. So I make it negative parentheses 2x plus 2 cosine x plus 2 integral cosine x dx. Okay, so what happened? I started with first degree trig function, and now I got it down to a trig function. Okay. Normally, when you have a polynomial involved, that's what happens. Let me just show what the progression was. I had second degree trig function. If I integrate by parts once, I get first degree trig function. And if I do it again, I just get trig function. So every time you do integration by parts involving a polynomial, the degree goes down by 1. Okay. So let's say, I'm not going to give this to you. Let's say you started off with x to the 10th trig function. So if you integrate by parts once, the next time you'll get x to the 9th trig function. Do it again, x to the 8th trig function. Next time, x to the 7th trig function, and then 6, 5, 4, 3, 2, 1, and so on. Okay. So I would normally never make you go that far on a problem, although I might be willing to have you go, let's say, 3 levels on a quiz. Okay, so maybe on Friday's quiz, I might make you go 3 levels. Start off with a cubic, let's say. So if a cubic, third degree, integrate by parts once, brings you to second degree, do it again, brings you down to the first degree, and then do it again, you finally got what you want. Okay, so all of this is I1. So now you pick up all of this stuff, which represents I1, and you bring it back here. Okay, again, you computer science people know this concept, right? It's like I have to stop and figure this out, okay? Do a sub-routine, sub-program to figure this out, and then go back and bring it over here. So now the original integral is this stuff, minus whatever I got from I1. So finally, the original I1 is this stuff, x squared plus 2x sine x minus something. So I'm going to copy this, x squared plus 2x sine x minus something. Let's see. Yeah, x squared plus 2x sine x, and then minus something, but that minus something has a negative there, so I decided to distribute this. So that becomes a plus, that becomes a minus. So plus 2x plus 2 cosine x minus 2 sine x plus a constant. Okay. In case you're wondering, when you distribute a constant, like you have negative c, that's still plus c, or plus 2c, that's still c. C is any arbitrary real number. So 2c is also any arbitrary real number. So the final answer, you can just put plus c. All right. So here's a case where you have to integrate by parts twice. All right. This is not an actual homework problem, although it's related to one of the homework problems. What is actually the integral of ln x? So now I'll show you the derivation for the integral of ln x dx. Okay. You probably didn't have that in Calc 1. Okay. Calc 1, you asked what was the derivative of ln x, 1 over x, but now what's the antiderivative? To get it, you integrate by parts. So you don't really have much choice here. Let u be ln x, and dv is the rest. Well, the rest is just dx. So u equals ln x, dv is dx. Differentiate, integrate. So du equals 1 over x dx, integrate, v equals x. Remember, you can pretend there's a 1 here. Integral of 1 dv, integral of 1 dx, you get v equals x. Okay. By the way, this is almost like the backwards of something we had before, that u equals x. Yeah, u equals x, du equals dx. On a grander scale, you just put a d on both sides. If I can coin a verb, it's you d both sides, right? Just put a d in front, d in front. Here's like you anti-d both sides. Take off the d. Just take off the d and you have v equals x. Anyway. All right, so integral using the same formula is uv, that times that, x ln x, minus the integral of v du. So v is x, du is 1 over x dx. Here, x's cancel out, so I'm just integrating 1. So integral of 1 dx is just x. So final answer, x ln x minus x plus c. Okay, so an antiderivative of natural log of x is this. You can see it's a lot clumsier. Okay. Even when we're meeting face-to-face, I would not have my class memorize this. Okay, I think it's too much to memorize. So antiderivative ln x is this. Not the derivative. Derivative is 1 over x. We know that. But antiderivative, and antiderivative ln x is x ln x minus x plus c. Okay. And by the way, that's easy to check. Okay, so let's run through the check. That means if this is correct, the derivative of this should be ln x. Let's try it. So derivative of constant is 0. We know that. X ln x, that's the product root, isn't it? So first x times the derivative of the second, 1 over x, plus the second function, ln x, times the derivative of the first, derivative of x is just 1. And then minus 1, derivative of negative x is negative 1. Okay, these x's cancel out, right? So this becomes 1, which cancels that 1. And yes, indeed, you have ln x. Okay, and these two lines mean end of proof. So yes, indeed, the derivative of this is ln x, which means the integral, antiderivative of ln x, is x ln x minus x plus c. Okay, so this is an antiderivative of ln x. And by the way, if you want to put this on your cheat sheet, you may. Okay, this comes in very handy for a question like problem 9. Nope, actually 9 star. That's right. This is not in our book. This is in the previous edition. But it's a good problem nonetheless. Okay, so how do we integrate ln of cube root of x? This might show up in another problem. But anyway, from algebra, treat this as ln x to the 1/3. And then you might recall that 1/3, by properties of loss, can come down in front. Well, if it's going to come down in front, might as well bring it all the way out. So I just have 1/3 integral of ln x. And now I know what this is. I just did that over here, right? So I have 1/3 of x ln x minus x plus c. So there we go. So this is often a trick you have if you have ln of x to some funny power, just get rid of the power, right? Cube root of x, square root of x, x to the 27th. Okay, you can always do this trick. All right, let me go back and do number 1. I did not do number 1 earlier. I did a 1 star, which was in the previous edition. But this is actually in our book, x e to the 2x. Yeah, x equals e to the 2x. Okay, so this falls in the category of polynomial times exponential. Again, let u be the polynomial part. X e to the 2x. So let u be the polynomial x, and dv is the rest. The rest is e to the 2x dx. Differentiate, integrate. du equals dx. V equals, okay? So I want you to try to get the idea of the chain rule inverse. Yes, you could integrate by substitution, but I don't think you have to if you just think of what you did when you differentiate it. Okay, back in Calc 1, what's the derivative of e to the 2x? Well, you would go e to the 2x times 2, right? By the chain rule. Make sure you understand that, because if you don't remember the chain rule for derivatives, you're not going to get what I say for the integrals either. From the chain rule, the derivative of e to the 2x is not just e to the 2x. Remember, you have to differentiate the exponent floating up there. So the derivative of e to the 2x is e to the 2x times 2. All right, so what did we do? We multiplied by 2. Therefore, when you integrate, you don't multiply by 2, you will divide by 2 or multiply by a half. Okay, so 1/2 e to the 2x. And again, I hasten to add, that rule only works for constants if you end up multiplying by a constant, not a variable expression. That's not going to work, but for constants, it's true. Remember, how do you double check? What is the derivative of this? The derivative of this is the same thing times 2. Well, that 2 is going to knock out the half, and voila, you get that. It works. All right, so throw it into the formula. So this is u dv, the left side. So u times v, that times that, 1/2 x e to the 2x. And by the way, normally you don't care about how bad this comes out to be because you're not doing anything with it. Okay, so this can have all kinds of weird stuff, exponentials, logs, trig. Okay, I don't really care because in the formula, you just have uv. You're not asked to differentiate that. You're not asked to integrate that. Just put it. So I'm not concerned about how complicated this expression is. You're just putting it. You're not integrating or differentiating it. I am concerned about how this is because I do have to integrate this part. All right, so minus the integral of v du. So v du is 1/2 e to the 2x dx. Okay, so here's my uv. Here's v du. And again, it did get better. Okay, I started off with x times exponential. After I integrate by parts, I just have exponential. And that's typically what happens. Okay, so let's say I started off with x cubed exponential. Then integrate by parts, you get x squared exponential. Do it again, x exponential. Do it again, then just exponential. You finally got it down to something you can deal with. All right, so leave that alone. That 1/2 is that. Okay, this 1/2 is this 1/2. And where did that other half come from? That comes from integrating e to the 2x. Well, we just did that over here, right? It's 1/2 e to the 2x. So the antiderivative of e to the 2x is 1/2 e to the 2x. So you're going to have a half times a half. And one more time, that half matches that half. And this other half comes from integrating e to the 2x. And of course, half times a half is a fourth. So final answer, the integral of x e to the 2x dx is 1/2 x e to the 2x minus 1/4 e to the 2x plus c. And that's the final answer. Okay. And again, one thing if you want to verify is to go ahead and differentiate this. I won't bother right now. But if you take the derivative of this, you should get back that thing. Okay. All right, so we're doing integration by parts. All these problems that are here. Okay, later on, we have some definite integrals like 23, 25, 27, 29. definite integrals aren't really that much more difficult. You just plug it in, that's all. Okay. Let's see some of those in time too. And let's see, before doing that, I'll show you quickly. Techniques of integration on page 471. There's a whole table here of antiderivatives. And I leave it to you. You may put these on your cheat sheet, but a lot of these are just backwards from what you remembered from trig, right? Okay. So the integral of sine is negative cosine because the derivative of negative cosine is sine, right? Integral of secant squared is tangent because the derivative of tangent was secant squared. Right? Most of these are backwards. Okay. Cinch and Cosh were derivatives of each other, therefore they're also integrals of each other. Okay. Some things you may not be as familiar with are integral of tangent, ln absolute value of secant of x plus c. That can be done using a substitution. Let it tangent be sine over cosine. Okay, and you can do that. Integral of cotangent is ln absolute value of secant x. Okay, and some of these other ones that are here. So you can put them down. I do want to spend a little bit of time about Cinch and Cosh because some of your Calc 1 teachers may have just glanced through it quickly. My class, my Calc 1, some of you had me for Calc 1. I did spend some time with that. So I wanted to go over that now in case you did not have that very much from your Calc 1. So the H stands for hyperbolics. Okay. And there was a whole section on that in Calc 1 3.11, I believe it was. I will check that for you. 3.11, hyperbolic functions. And it started off with, yeah, page 259, 3.11, hyperbolics. Okay, so just in case your Calc 1 teacher didn't spend too much time on it, I'll go through the basic definitions. So you have the 6 trig functions, sine, cosine, tangent, cotangent, secant, cosecant, and you just put an h at the end. So sine h, cos h, tan h, this stands for hyperbolic. So officially, hyperbolic sine, hyperbolic cosine, hyperbolic tangent. It's kind of hard to even say. This one I normally just say cinch, cinch x, cosh x. Okay, it's kind of hard to say some of the others. But cinch is e to the x minus e to the negative x divided by 2. Cosh, or sometimes cosh, is the exact same thing, except instead of a minus, it's a plus. And in my opinion, once you have these two, the rest just follow naturally. Because what do you think hyperbolic tangent is? Well, just like in trig, is hyperbolic sine over cosine. So that divided by that, the 2's will cancel out. Cinch over cosh. So e to the x minus e to the negative x divided by e to the x plus e to the negative x. Cosh, hyperbolic cotangent, is hyperbolic cosine over sine. So I just flip this thing. And yes, hyperbolic secant is a reciprocal of cosh. So 2 over e to the x plus e to the negative x. And hyperbolic cosecant is a reciprocal of cinch. So I just flip this guy, 2 over e to the x minus e to the negative x. Okay, so I have this, it's there. I would probably say if you need to put something on your cheat sheet, put these two. You're welcome to put these on your cheat sheet, but that's taking up extra space in my opinion. If you know the rules from trig, you should be okay with these because, the hard part I think is just have these, but you should already know, oh yeah, tangent is sine over cosine, so cinch over cosh. And hyperbolic cotangent, flip that. And hyperbolic secant, cosecant, just like in trig, flip that one and flip that one. And the only important derivatives, in my opinion, are derivatives of cinch and cosh are each other. Derivative of cinch is cosh, derivative of cosh is cinch. And derivative of hyperbolic tangent is hyperbolic secant squared. That's almost exactly like trig, right? In trig, derivative of tangent was secant squared. So derivative of hyperbolic tangent also turns out to be hyperbolic secant squared. And then just for fun, I have this cinch of 0 by definition, plug in 0. E to the 0 minus e to the negative 0 divided by 2. 1 minus 1 over 2, 0. Cosh of 0 is e to the 0 plus e to the negative 0 over 2. 1 plus 1 over 2, 1. Okay, so that's that. And you may recall from trig, sine of 0 is 0. Turns out sinh of 0 is also 0. And from trig, you might remember cosine of 0 is 1. So cosh of 0 also turns out to be 1. But that's only for the special angle of 0. That's not true in general. Right? So if I pick any other angle like pi over 2, they're not going to match in general. So all of that, finally, we can get started with 25. A definite integral, 0 to 1, t cosh t dt. Okay, so this is a definite integral, which means the answer will have a definite number. But otherwise, you do the same thing. Right, so we had a root. Generally, if you have a polynomial like t, let that be u. So u equals t, dv is the rest. So here's my u, here's my dv. Okay, differentiate, integrate. U equals t, du equals dt. And frankly, this part is pretty easy. It's almost like you just put a d on both sides. You are differentiating, but if you want something quick and dirty, put a d here and a d here. Du equals dt. On a deeper scale, yes, the derivative of u with respect to t is 1. So you could say du dt is 1, multiply both sides by dt, and it looks like that. Okay, and integrate this side. V is sinh. Integral of cosh is sinh. Okay, now, this is just a little bit different. Okay, so by formula, I do the uv part. Uv. Difference is that this time it's a definite integral, so I'm supposed to put 0 to 1 here. Okay. U times v, t sinh t from 0 to 1. Okay. Put this outside again on the right-hand side. Okay. This part we haven't finished integrating yet, so I leave it inside. Minus the integral of v du. Integral of v du. So v is sinh, and du is the same as dt. So here I finished integrating this side. So the normal convention, stick it over on the right side, straighten it out. But this one stays on the left side with a funny looking s, 0 to 1. And yeah, now what's the integral of sinh cosh, which is the reason why I went through this. Now I write as t sinh t minus cosh t from 0 to 1. And now I plug in 1 sinh 1 minus cosh 1. So it's sinh 1 minus cosh 1 minus, plug in 0. Okay, that makes that 0. Cosh of 0 turns out to be 1. So it's sinh 1 minus cosh 1 minus a minus 1. So final answer, sinh 1 minus cosh 1 plus 1. And just leave it like that. Now you might say, what is sinh 1? I don't know, plug it in. E to the 1 minus e to the negative 1 divided by 2. So it's like 2.7. E is like 2.7, right? 2.7 minus 1 divided by 2.7, and take that whole thing and divide it by 2. And cosh 1 would be same thing, roughly 2.7 plus 1 over 2.7, divide the whole thing by 2. So there's that. All right, 31. What time is it? 8:45-ish. Okay, integral from 0 to half of inverse cosine dx. Okay. You might say, what is an integral of inverse cosine? Oh no, it's integrate by parts. Okay, so let u be that part, and dv is the rest. Really isn't much choice here. Please notice again, it's a definite integral. Let's see. I think I have it wrong. No, this is not our 31. Oh, because I got to say it's 31 star again. Meaning it's not the real 31. But it's good to know how to do this anyway. Okay, let that be u. dv is the rest. Okay. du, do you recall the derivative of inverse cosine? It's the same as the derivative of inverse sine, except there's a negative. So it's negative 1 over radical 1 minus x squared dx. Integrate v equals x. Okay. It's almost like you take off the d, or anti-d both sides. Once you get something like this, v equals x. So I is uv x inverse cosine x minus, okay, so pretend it's a minus sign. There's a reason why I changed it. Integral of v du. V du has a negative 1 times x. So pretend these are both negative. And then in red, I don't know if you can see the red, I quickly change it to positive. Over radical 1 minus x squared dx. Okay, so uv x inverse cosine x minus, pretend it's a minus, integral of v du. There's a negative there, so negative x over radical 1 minus x squared dx. Okay, and decided to call this I1. Change that to a plus. So it's x inverse cosine x from 0 to half plus I1. Okay, so let me get this out of the way. I plug in, well, if you plug in 0, you get 0, right? 0 times that is 0. Okay, plug in a half. 1/2 inverse cosine of a half. Okay, inverse cosine of a half. What angle is there? Nice angle between 0 and 90 degrees, such that the cosine of the angle is a half. Well, that's 60 degrees. Okay, so I remember inverse cosine. Cosine controls the x coordinate. I go over halfway and look at that angle. That looks like 60 degrees, so pi over 3. So 1/2 of pi over 3 or pi over 6. Okay, so my answer is going to be pi over 6 plus whatever I get for I1. Okay, so now again, I have to take a time out and figure out I1 here, which has integral of x over radical 1 minus x squared. That looks like my u substitution. Okay, so at the end of Calc 1, you were doing u substitutions. I noticed the derivative of 1 minus x squared is a negative 2x. I have an x here. I can take care of the negative 2 quite easily. Okay, so u equals 1 minus x squared. Du equals negative 2x dx. Okay, x is going from 0 to a half, so I have to plug in. So when x is 0, plug a 0 in here, u is 1. Plug in a half. 1/2 squared is 1/4, so 1 minus 1/4 is 3/4. So I1, oh, and yeah, the original was like this. I see the x and the dx. I need a negative 2 inside. So negative 2 inside, negative a half outside. So I have negative a half integral from 1 to 3/4 of du over radical u, right? Negative 2x dx is my du. Square root of 1 minus x squared, square root of u. And this happens a lot. Negative here, bigger number, smaller number. Okay, we're used to having it the other way around, so I just switch it. Make this a positive, turn these around, and I have the best of both worlds. This is positive, this is smaller than this. All right, square root of u on the bottom means u to the negative half. So if I integrate, that's u to the 1/2 divided by a half. Divided by half means multiplied by 2. Very conveniently, these drop out. Okay, u to the half means square root. So plug in 1, square root of 1. Plug in 3/4, square root of 3/4. 1 minus square root of 3 over 2. Okay. All of this is my I1. Okay, so that I1 goes way back here. So I now have pi over 6 plus I1 as my final answer. So pi over 6 plus I1, 1 minus radical 3 over 2. Okay, and then over here, I just did my common denominator thing. So common denominator is 6, leave that alone. 1 is 6 over 6, multiply top and bottom by 3. So here's my best final answer. Pi plus 6 minus 3 radical 3 all over 6. Okay. So that was a little bit weird. Okay, one last one that I will show you was 37. It says first make a substitution and then use integration by parts to evaluate the integral. So what do they mean by that? cosine radical x. All right, I don't like radical x. I like it to just be t. So that t be radical x. Square both sides. So it looks like this. T squared equals x. Now I differentiate both sides. Okay. So 2t dt equals dx. Right? This is using the Leibniz notation in differentials. Right? Take the derivative, put dt, take derivative, dx, derivative of x is 1. Okay? So now right here where it says dx, I'm going to put in this stuff. So I have the integral of cosine radical x, which is cosine of t, and then dx, 2t dt. Take out the 2, and I now have integral of t cosine t dt, and this one I integrate by parts. But there's a 2 in front, so I have to remember the 2. So I is 2i1. The original integral is 2 times whatever I get when I figure out I1. All right, so that u be t, again, it's a polynomial times the trig function, let u be the polynomial. U equals t, dv is cosine t dt. Differentiate, integrate. Du equals dt. Anytime you just see something like this, u equals t, u equals x, just put the d's there. And similarly, if the right-hand side comes out to be something like this, dv dx, just take off the d's, v equals x. Right, so u equals t, dv is cosine t dt. Differentiate, integrate. Du equals dt. Integrate, integral of cosine is sine. Okay, careful, integral of cosine is sine, not the derivative. Derivative of cosine is negative sine, but the integral of cosine is sine because the derivative of sine is cosine. Okay, so I1 is uv, t sine t, minus the integral of v du, so sine t dt. So I'm integrating negative sine, essentially. The integral of negative sine is positive cos. So t sine t plus cosine t plus c. Right, that's I1. I, the original integral, is 2 times that. So 2 times t sine t plus cosine t plus c, and then change t back to what it was. T was radical x. So everywhere I see t, make it radical x. So I distributed also 2 radical x sine radical x plus 2 cosine radical x plus c. Again, word of explanation. Yes, plus 2c, but c is any arbitrary real number. So 2c can just be put down as c. In fact, you should put it as c. That's the most general way to write the answer. So not plus 2c, just plus c. So there we have for that. Okay, so that's a lot of integration by parts. I think that's all I was going to do for today. So let me stop the share and check if it's anything in the chat. And if not, we can call it a day. Okay, so anybody here want to ask any questions, please? All right, see nothing and hear nothing, so we'll call it a day. All right, everybody, have a good day, and we'll see you next time. Okay. All right, bye, everybody.
Thank you.
Thank you.
Okay.